Hello, welcome to the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is a part 4 of an 8-part little mini-series within that playlist that I'm calling Balanced Two-Factor Factorial Design with Interaction. In this video, we're going to look at the distribution of the sums of squares and f-tests. Now, as a reminder, our model is x star, beta star, plus epsilon. So it is a linear model, and then we can partition that into mu times the one vector, x alpha plus, etc. And I'm going to encourage you to look at parts 1, 2, and 3 for more detail about the model and the model development. Now, the sums of squares, for the distribution of sum of squares, I'm going to pass you off to a video that I call Distribution of Quadratic Forms. It's in a quadratic playlist that I have. It's actually something that every statistician should have in their tool bag, so I would suggest you watching that. But one note, what I do to make using these formulas easier, I look at the distribution of 1 over sigma times y, and then that's distributed with multivariate normal, with this mean, and covariance matrix I. And when this is I, it makes using these theories easier. Not impossible, and it's actually sort of straightforward if you don't, you just look at y, but then you have to show certain matrices are idempotent, and it's just easier just to leave it out in this case. So the sum of squares there, if we look at this, so y over sigma, those are multivariate normal, and this is the matrix in the middle. So the theorem, one of the theorems says that it's a chi-square distribution with these degrees of freedom equal to the rank of this matrix, which we proved was AB times n minus 1. So it's a central chi-square because the non-centrality parameter, it ends up going to 0. Now the sum of squares for treatment A, we look at this, but really remember we think about it as those sigmas under each y. And so this is the matrix in the middle. So it is a non-central chi-squared with a minus 1 degrees of freedom, right? That's the rank of m alpha minus j. And then the non-centrality parameter has this scalar representation. And in part 3, we showed how to take the matrix form of this and put it in this scalar notation. And I'm writing it in scalar notation because it's going to help illustrate a couple ideas that I have at the end of this video. Now, sum of squares for treatment B is very similar. It's y transpose mb minus j, y divided by sigma squared. It's a non-central chi-square distribution with b minus 1 degrees of freedom and this non-centrality parameter. And again, we derived this scalar representation in part 3. Sum of squares for interaction is this, so it's y transpose the perpendicular projection matrix onto that interaction space, m alpha beta minus m alpha minus beta plus j. It's a non-central chi-square distribution with a minus 1 times b minus 1 degrees of freedom, has this non-centrality parameter. And again, we derive that in part 3. Now, I mentioned that the degrees of freedom in each case is actually, it's the rank of that matrix in the middle. So it's the rank of this, which we also proved in earlier videos. And that's how the degrees of freedom is derived. Now, when we're conducting tests, we have to show that the numerator and denominator quantities are independent. And to do that, we have to show that the matrices in the middle of the quadratic form are 0. And if they're 0, then they're independent. And this is the matrix in the middle of the sum squared error, right? And then we're taking it times each of these and to show that they're independent. And that's what we're doing here. But notice that each one of these projects onto the column space of x. So all of these are within the column space of x. So when you pre-multiply it times I minus m, which is a perpendicular projection matrix on the orthogonal complement space of x, it's 0, has to be 0, because it projects everything into the orthogonal complement. And only vectors they have in common are 0, so this has to be 0. And you can actually, if you look at part 2, and you multiply each of these out and each of those out, you get a cancellation so that it goes to 0. Same way you could do that and FOIL it out. That's what my daughter would call it. Now the test for interaction. Whenever you have an interaction model, that's generally the test you do first to see if there's significant interaction. And notice that I'm going to go back here. So here's the sum of squares error and the distribution associated with it. Now we want this non-centrality parameter to be 0, and that's what actually all these tests do. Is that the null hypothesis is that this non-centrality parameter is 0, and then the test statistic ends up being a central F random variable, and we make a test. So the null hypothesis is that this is 0. So this term, the alpha beta ij term, minus minus plus, is all 0. And so this is what we put in the null hypothesis. Now, instead of saying equals 0, I just took everything else to the right side, and we have alpha beta ij equal to this. So this is the no interaction effect. Of course, the alternative is that there is or that they're not equal, and meaning that there is interaction. So here's what I wanted to show you. So let's assume that the null hypothesis is true. So then we can write out the model as this. So remember, this is our original model. So yijk is equal to this. But if this is true, we can put this in for yij, and that's what we do here. Now notice there's no index here, so we can group that with this one. There's only an I index here, so we can group it with alpha I. There's a beta, there's a j here, so we can group it with beta j. Now these are parameters, so let's just kind of call them something different. So let's just call this mu star, right? This is a constant with, there's no index. So here, let's just call this alpha I star, right? Because only the I indexes are there, and this beta j star and the error term. So notice that this is an additive model, and that's actually what we're trying to test. Is there interaction? And if the null hypothesis is true of no interaction, it reduces to an additive model, right? There's no interaction term here, right? And if these were not equal, then this would have stayed an interaction model. Okay, so then the test becomes the mean square for interaction. So it's the sum of squares, alpha beta, which divided by its degrees of freedom, which is the mean square for interaction, divided by the mean squared error. And under the null hypothesis, this is a central F random variable, so we can conduct the test. Now, what is interesting is, we've all heard that, if there's interaction in the model, the main effects tests do not make sense. So let's illustrate that and show exactly why it doesn't make sense. So we're going to do a test for the main effect A. So let's look at page 1 here again and look at the sum of squares for treatment A. And so this is divided by sigma squared. So this is a non-central chi-square random variable distributed like this. So in the null hypothesis, we want this non-centrality parameter to be 0, right? So we're going to set it equal to 0 every term for all I, right? It's only indexed by I, which is kind of nice. So that's what we're setting to 0, and that's what we want, right? So that's actually the null hypothesis, is that there's no, well, I don't want to say there's no main effect for factor A, because it doesn't make sense. But if we put that equal to 0, which then I took everything to the other side except for this alpha I, and then that should be not 0 for some I. And here's our test statistic, mean square for treatment A divided by mean square error, and under the null hypothesis, that's a central F random variable. We can conduct a test. But what does that get us? What does it even mean? So if we look at if we assume that H naught is true, so under H naught, then that means this is true. So we can plug this in for alpha I. So here's our original model. So we plug in what the null hypothesis says, and we try to group, so there's no index here, and there's no index here, so we can group all those together. There's an I here, beta j alpha. So we can call this mu star and call this alpha I star, and then the beta j in the term. But what has changed? I mean, how do we interpret in accepting H naught? And so it's still an interaction model, and there's still, you know, there's still the term for the main effect in here. And so rejecting H naught does not lead to a different model. And so it doesn't make sense, or that test doesn't make sense. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.